Here we go with part 2 of the chapter 11 lecture. So when last we left, we were about to start colligative properties. So a colligative property is something that does not depend on the type of particles in solution, but only on the number of particles in solution. Okay, so sometimes the identity of the compound matters because it will affect a chemical reaction of some sort. But in this case, colligative properties are things that only depend on how many particles are in the solution. So the first one is freezing point depression. So that means, essentially, that means lowering of the freezing temperature. Okay. Boiling point elevation, that one is raising the boiling point temperature. Okay. And osmotic pressure is actually one that those of you that are interested in medical fields is actually important, because osmotic pressure is part of what keeps our cells in the right shape and size, because osmotic pressure is the tendency of water to flow. Okay, and in the case of like human cells, like human blood cells, for example, water wants to flow from areas of high concentration to areas of low concentration. So if all of the water in, say, your red blood cells flowed out of the red blood cell, you would have a flattened, deflated blood cell. But in the other direction, if water flowed completely into the blood cell, it would burst. Okay, so osmotic pressure is an important thing for a lot of biological systems. So the reason that we have this image here of like a frozen lake is a reminder of some of the reasons that we are using colligative properties. So in the wintertime, we put salt on frozen surfaces, right? Whenever we get icy sidewalks and things like that. Because when we put the salt down, it mixes with the water layer and makes it salt water. And salt water freezes at a lower temperature than regular water does. And so what we get is it keeps mixing, and that salt water stays water instead of freezing. Okay. Boiling point elevation, those of you that are in the habit of adding salt to your water when you make noodles and things like that, the reason you do that, aside from because my mom said so, is because when you add the salt, it causes the water to boil at a higher temperature. Okay, so when you add particles in, it changes the physical properties of the new solution. Okay, so let's talk a little bit about a thing called electrolytes. All right, and most of you are aware of what an electrolyte is, at least in terms of, Gatorade has electrolytes and things like that. But in order to be an electrolyte, a component must be ionic. Okay? Anything that's not ionic cannot be an electrolyte. Okay? So let's take a look at the compounds that we have in this list. Okay? In order to be ionic, it must have a metal, right? So which of these compounds does not have any metals, right? So potassium, that's a metal. Iron, there's a metal. Sodium, there's a metal. NH4, that's an ion, okay? So NH4 and Cl, those are two ions. So NH4Cl is an ionic compound, ammonium chloride. CH5N has no ions and has no metals, right? So the one that has no ions and no metals is the non-electrolyte, okay? Call this a non-electrolyte. Kind of misjudged the length of that word right there, okay? And the red answer tells us we are correct. Yay! Okay, so why do we? One of the things that we need to know about in dealing with colligative properties is how many ions are there in your solution. Okay, when we add, say for example, some sodium chloride to some water, and we get, say, a 1 molar solution of sodium chloride, what is the total concentration of ions in that solution? Okay, because the ions, we basically refer to those, we can also refer to those as particles. Okay, so with colligative properties, the colligative property changes by the number of particles that go into the solution. So if we have an ionic substance, it's going to come apart in water, and we're going to get particles. Okay, so for example, one of the things that you need to be able to do is to be able to determine how many ions are there per molecule. Okay, so looking at sodium chloride here, sodium chloride comes apart into one sodium atom or ion and one chlorine ion. So we get 2 ions per sodium chloride. Okay, so I can also say 2 moles of ions per 1 mole of sodium chloride. Okay, those are the same thing. So if I start with 1 molar sodium chloride and I want to know how many ions there are total, what is the total ion concentration? I can just multiply by the number of ions. Tells me that I have 2 molar ions in solution. Okay, so your task is to determine how many ions there are per molecule. So let's look at our next example, 3.2 molar calcium chloride. Calcium chloride comes apart into 1 calcium ion and 2 chlorine ions. So I get a total of 3 ions per molecule. So in order to find out how many, what is the ion concentration for 3.2 molar calcium chloride, I multiply times the number of ions. It's not 2, it's 3. Okay, means that I have 9.6 molar ions. Okay, so why do we care? Because more ions gives either a higher boiling point, a lower freezing point, or higher osmotic pressure. So if you're given a list of solutions, you need to be able to tell which one will give you what you're after. If it's asking for which gives a higher boiling point, or which gives the lower freezing point, or which gives the higher osmotic pressure. Okay. Now, one more example would be something like if we had 2 molar C6H6O2. Okay. Is it ionic? And the answer is no. Okay. This thing does not come apart in water. Okay. This is actually a version of sugar. I think it's sucrose or something. Don't quote me on that. But if it does not come apart, that equals 1 particle. Okay, I just get the molecule itself, right? So total concentration of particles times 1 particle equals 2 molar particles. Okay, because it's not ionic, it doesn't come apart. Okay, so which solution has the lowest melting point? So remember, melting and freezing are basically at the same place. So melting and freezing happen at the same temperature. Okay, for water, for example, water melts at 0 degrees, but it also freezes at 0 degrees. It just depends on which direction you're going. So the lowest melting point would be the same thing as the lowest freezing point. Okay, and remember, more ions equals lower freezing, because it's freezing point depression is the colligative property. Okay, so let's look at our first option here. So sodium chloride has 2 ions per molecule. So that means that I've got 2 molar ions there. Same thing here, so that gives me 4 molar ions with that solution. Okay, NH4Cl, ammonium chloride, that's NH4 plus and Cl minus, so there's 2 ions there, so it's also 4 molar. Aluminum chloride, that's 1 aluminum ion and 3 chloride ions, so there's 4. So that gives us 8 molar. And NH4,2CO3, that means that we have 2 NH4 pluses and 1 CO3 2 minus. So that means there's 3 ions there. So times 3 gives us 6 molar ions. So the one with more ions gives us the lowest freezing point, or the lowest melting point. Okay. So highest osmotic pressure, that one is related to more ions equals higher osmotic pressure. Okay, so same process. Potassium chloride has 2 ions, so 1 potassium ion, 1 chlorine ion, 4 molar ions there. Potassium nitrate, remember that's K plus and NO3 minus, so there's 2 ions there, so also 4 molar. NH4NO3, that's ammonium, NH4 plus and NO3 minus, so 2 ions there, gives us 6 molar. NH4,3PO4, that should be all in one line, sorry. So that gives us 3 ammoniums and 1 phosphate, so that's times 4 ions, gives us 8 molar. And 1 molar barium chloride, that gives 3 ions, 1 barium and 2 chlorines, so that gives us 3 molar. Okay, so our winner is the 2 molar ammonium phosphate. Okay. So now, interesting question, this one. Okay, so osmotic pressure, okay, is water's tendency to flow, okay, in one direction or another. And the trick is that water flows, let me change colors here, this is a little boring. Okay, water will always flow toward higher concentrations. Okay, because water wants to distribute the concentration. Okay, so if water can flow into the area with more concentration, that's the same thing as diluting that higher concentration. So water is going to move so that it can dilute the higher concentration. Okay, so in our diagram here, we have this membrane right here in the middle. So the membrane keeps the ions separated, but water can flow through the membrane, whichever direction it wants to go. Okay, so on the left, we have 3 molar sodium bromide. So ion concentration on the left is 6 molar ions, right? On the right, we have 1 molar sodium sulfate. So that gives us a 3 molar ions. Okay, so the side that has more ions, that's higher concentration. So the water is going to flow towards the higher concentration. Okay? So it's going to flow towards the NaBr solution. Okay. Which aqueous solution has the highest boiling point? So highest boiling point is most ions. Okay. So here we have times 2 ions, gives us 0.6 molar ions. Right? K2SO4, there's 3 ions there, 2 potassiums and 1 sulfate. So that gives us a 0.45, right? Potassium phosphate, there's 3 potassiums and 1 phosphate, so that's times 4. Potassium carbonate, that's 2 potassiums and 1 carbonate, so there's 3 ions there, equals 0.45. Right? So the most ions has the highest boiling point, and that is the potassium chloride solution. Lowest freezing point, again, this is most ions. Right? So this is challenging your nomenclature here. So magnesium nitrate, that's MgNO3 2. So that one's going to have 3 ions, so we get a 0.3 molar for that one. Sucrose, that's a non-electrolyte. Okay, that one has no metals and no ions. So we get 1 particle for every molecule, right? So this one's just times 1. So 0.1 molar here. Okay. Aluminum nitrate. Aluminum nitrate should be an AlNO3 2. So we get, excuse me, not a 2, a 3, my bad. NO3 3. So we get 4 ions, so we should end up with 0.4 molar here. And sodium nitrate, that's going to come out as NaNO3. So we get 2 ions there, so a 0.2 molar. All right, so which one has the most particles? That would be the aluminum nitrate. Okay. So our next topic is we're going to sort of get away from this ion business and the colligative properties for a little bit. And we're going to talk about different types of reactions in solution. Okay? So previously we've done some of this, and you've seen all of these reactions before. We've just used slightly different terminology for them. Okay? So precipitation reactions, remember we did these when we did ionic equations. Right? Remember doing complete and net ionic equations and dealing with solubility rules and all that stuff? Okay, so we're going to bring that back around. Acid-base neutralizations, right? Remembering that acids start with H, right? And bases, I'm going to do this down here, and bases have an OH generally. Okay, so you need to be able to recognize when you're dealing with acids and bases coming together. And then the metal displacement, you've seen that one before, but we've called it a single displacement reaction. Okay, so you'll recognize all 3 of these reaction types. Okay, so this should be an arrow. Sorry, sometimes when I put these things in my in my device, the symbolism doesn't always come with me. All right, so when I put two aqueous things together, the last time we saw this, what did we do? We did a double displacement reaction. Right? So I'm going to trade both of the metals. I'm going to take the sodium and put it with the chlorine, and the aluminum and put it with the phosphate. Okay, and just to remember how that goes, we're going to be putting a sodium plus and a chlorine minus, and then we're going to have an aluminum 3 plus and a phosphate 3 plus, or excuse me, 3 minus. Okay, so I just want to correctly combine those things on the other side. So I'm going to have NaCl, because it's a 1 and a 1 plus and a 1 minus, and just aluminum phosphate, because it's a 3 plus and a 3 minus, so I just need one of each. Okay, then we balance. Right, let me take this stuff out of the way here. Okay, so then we balance, right? So I've got 3 sodiums on the left, so I need 3 sodiums on the right. And that gives me 3 chlorines on the right, and I already have 3 chlorines on the left. I have 1 aluminum on the left, 1 aluminum on the right, and 1 phosphate on the left, and 1 phosphate on the right. Now, because this is two aqueous things together, we need to figure out if one of them makes a solid. And if you check back with your solubility rules, we find that anything with sodium is soluble. Okay? And then phosphates are generally insoluble. Okay? So let's look at our next one. So again, this is two aqueous things, right? And this one on the right here is lead acetate. Okay, and acetate is a 1 minus. Okay, so I'm going to take and put my lead with the chlorine and my magnesium and put it with the acetate. Okay, so that means that I've got a, now if acetate is a 1 minus and I have 2 of them, then that means that lead is a 2 plus. Right? So I'm going to have a lead 2 plus chlorine minus, and I need to put those together correctly, and then I'll have a magnesium 2 plus and an acetate, C2H3O2, 1 minus. Okay, so we want to put those two things, those two pairs of things together correctly. So my lead is a 2 plus, so that means that I need 2 chlorines to go with it. Okay, and then my acetate is a 1 minus, and my magnesium's a 2 plus, so I need 2 acetates. C2H3O2, 2. Okay. All right. So now I go through and I balance. All right. So I've got 1 magnesium on the left, 1 magnesium on the right. Good. I've got 2 chlorines on the left, 2 chlorines on the right. Good. 1 lead on the left, 1 lead on the right, 2 acetates on the left, and 2 acetates on the right. So everything is balanced. Then we go through and we do our solubility, and all acetates are aqueous. My goodness. Okay. And lead with chlorine makes a solid. Okay. Now acid-base neutralizations, and again this should be an arrow. All right. So acid plus base always makes a water and a salt. Now remember that a salt is a generic term for an ionic compound. Okay, so any ionic compound, you can also refer to it as a salt. Okay, so magnesium chloride in this example has a metal and a nonmetal, so it's ionic. And we refer to it as a salt. Okay, so acid, take a look, starts with an H. It's dead giveaway that it's an acid. And then we have a compound with OH that makes it a base. So acid plus base makes water plus a salt. Okay, let's take a look at our ionic or our acid-base reactions here. Okay, so we have, starts with an H, we have an acid, has an OH, that's a base. Okay, and we know that one of our products when we have acid plus base is liquid water. Okay, now the beauty of these is essentially they are double displacement reactions. So I can treat them just like a double displacement. I can take my cesium and put it with my nitrate, and I take my hydrogen and put it with the OH. So that's how I get the water. H plus OH makes H2O. And then cesium is a 1 plus, and nitrate is a 1 minus, so I get cesium nitrate. And all nitrates are soluble. Okay, so let's treat the second one the same way. Let's take the hydrogen, put it with the OH, and take the magnesium and put it with the bromine. Okay, and we're going to have H plus OH, and we're going to have Mg2 plus Br minus. Okay, so again, I want to just simply put those things together correctly, and then we'll come back and balance. So we got H2O liquid as one product, and the other one is magnesium bromide, Br2. Okay, and then we come back and balance. Okay, so I've got, let's see, so I've got two OHs, so two oxygens on the right with the OH2, with this part right here. Right, so I'm going to need a 2 in front of my water to give me 2 oxygens. And that gives me 4 hydrogens. So 4 hydrogens on the right. Right now I have 3 hydrogens total on the left. But let's take a look. I need 2 bromines on the right and 2 bromines on the left. So let's take and put a 2 over here. And doesn't that give me 2 hydrogens with the HBr and then 2 more hydrogens with the OH? So that gives me 4 hydrogens total. And there's 1 magnesium on both sides. So there we go. All right, so let's do our third example. So KOH and H2SO4. Okay, again, I'm going to take the potassium and put it with the sulfate. So I'm going to have a K plus and an SO4 2 minus. And then I'm going to have an H plus OH. Okay, so again, it's double displacement. Hydrogen goes with the OH, potassium goes with the sulfate. All right, so we'll have H2O and K2SO4. And that will be aqueous. Anything with potassium is aqueous. So let's double check, see if we need any balancing. Let's see, we've got 2 potassiums on the right. So let's put 2 potassiums on the left. Okay, so that gives me 2 and 2. That gives me 2 OHs and 2 hydrogens. So that's a total of 4 hydrogens now. So I need a 2 here to balance those. And that takes care of my 2 oxygens there on the right and the left. I have 1 sulfate on the right and left, so we are balanced. Okay. So precipitation is essentially a double displacement reaction, and we get a precipitate from it. We get some kind of solid out of it. Okay, that's the defining characteristic there. Okay, acid base, recognize we've got an acid plus a base, and we get water and a salt. Okay, it's also a double displacement. And then metal displacement is simply you start with one solid metal on the left and a different solid metal on the right. Okay, so we just have a single displacement reaction right here. Okay. Let's take a look at some examples, see if we can figure it out. All right. So, are there any acids or bases? Do we have anything starting with a hydrogen or ending with an OH? And the answer is no. We do have some solids in there, but it's not from precipitation because I start with one metal solid and I end with a different metal solid. And that should be an arrow there too. Okay, so if I start with one metal solid and end with a different metal solid, we saw that right up here with metal displacement. So that must be our answer. Okay. Can't be combustion because there's no O2. Okay, it's not a synthesis because we don't have 2 or more things coming together to make one thing. We already talked about it's not precipitation and it's not neutralization. All right, let's predict our products. Okay. So check it out. I've got one metal solid all by itself here. So if I do a single displacement there, see what we get. We take and put a barium 2 plus with a bromine 1 minus. So we get a barium bromide, Br2. And that's going to be aqueous. And we get tin all by itself, right? And it is balanced because we've got one bromine and one bromine, one tin and one tin, one barium and one barium, one tin and one tin, and 2 bromines and 2 bromines. So we are good. So barium bromide and tin. So tin solid and barium bromide is B. Okay. Okay. When an aqueous solutions of sodium chloride and lead 2 nitrate are mixed, what precipitate forms? So this will be challenging your nomenclature. So we have sodium chloride, and it says aqueous, an aqueous solution of sodium chloride, and an aqueous solution of lead 2 nitrate. Okay. So do a double displacement, and we're going to have, so we're going to take and put lead 2 plus chlorine minus, and we're going to have a sodium plus NO3 1 minus. So we put those together in the correct ratios, and we get as products a lead chloride and a sodium nitrate. Okay. Now right away, anything with sodium or nitrate is aqueous. Right? That's an easy one. And let's balance. Let's make sure that we're balanced here really quick. So I need, I have 1 sodium on the left, 1 sodium on the right. That's fine. 1 chlorine on the left and 2 chlorines on the right. So I'm going to put a 2 here on the left. And that means that I need a 2 in front of my sodium on the right. And then I have 1 lead on the left, 1 lead on the right, 2 nitrates on the left, and now 2 nitrates on the right. Okay, so if we check the solubility rules, we find that our lead chloride, in fact, is a solid. Chlorides are soluble except with silver, mercury, and lead. Okay, what ionic compound results from the reaction of copper metal with aqueous silver nitrate? So we want to write out an equation. So solid copper metal, solid Cu plus AgNO3, it tells us that it's aqueous. Okay, so what type of reaction do we have when we are starting with a single metal and we do a single displacement? I'm going to trade places with the copper and the silver. And so I'm going to get solid silver instead and copper nitrate, which is probably the CuNO3 too. But it's not specific about what ion the copper makes. All right. Now, if we're being careful, let's go ahead and finish what we're doing. And anything with nitrates, those are all aqueous. Okay, and then let's finish and balance. So I need 2 nitrates on the right. That means 2 nitrates on the left, 2 silvers, and I need 2 silvers. Okay, but the question just wants to know what's the ionic compound, and that happens to be copper nitrate. Okay, that's this guy. All right, dun dun dun. Solution stoichiometry. Okay, so you already know all kinds of ways to convert various things into moles. Okay, so looking at the various types of things that we know how to do, one of the first things that we did from atoms to moles, and then the next thing was grams to moles, and then most recently we went from gas laws to moles. Now we have moles and liters, so molarity, solution to moles. Okay, but in the end, the stoichiometry part, this part doesn't change. That's moles to moles, right? Moles of one thing to moles of any other thing in the equation. Okay, but now we have all these tools in order to get to moles and get out of moles. Okay. So let's take a look at this particular question. So if 250 moles of milliliters of 0.1 molar calcium bromide reacts with excess potassium phosphate, how many grams of solid calcium phosphate will form? Okay. So in order to do the stoichiometry, I want to go from the potassium phosphate to the calcium phosphate. Right? So in order to do that, I need moles. Okay? So the mole ratio happens right here in the middle. Okay? So I want, and it's kind of small, so I'm not going to write it in there, but I want moles of calcium oh, I'm sorry, I misspoke earlier. We're going to take that out. We're actually going from the calcium bromide. My bad, because it tells the calcium bromide. Okay. The phosphate is extra, right? It's excess. So my bad. So here I want to go moles of calcium bromide. And then I want to get to moles of the calcium phosphate. Okay. All right, so let's go ahead and go through that process. So earlier in the chapter, when we were doing all that stuff with molarity, I tried to impress upon you that anytime you see that capital M in the problem, that means it's going to be used as a conversion factor. Okay. So the units of molarity are moles and liters. So right now I'm in milliliters. So let's do a quick conversion there. So 250 milliliters, and there's 1,000 milliliters in 1 liter. So that gives us 0.250 liters of the calcium bromide. Okay. So that's our that's our given information, right? That 250 milliliters. So this is given. All right. So that's what we're going to start with. And in the interest of space, I'm going to take that away for now. And that's where we're going to start. So 0.25 liters of the calcium bromide. Okay, so now I have this molarity, and the molarity is going to act like a conversion factor. So that's going to give me 0.100 moles of calcium bromide per liter. Okay, so my liters will cancel out, and that will give me moles of calcium bromide. So if I stopped here, that's what I would have. I would have this part right here. Okay, so now I'm going to do my stoichiometry. So this is where I use my mole ratios. So I've got 3 moles of calcium bromide and 1 mole of calcium phosphate. Okay, so right now moles of calcium bromide are on top, so I'm going to put them on the bottom. I'm going to put my moles of calcium phosphate, Ca3PO4 2, on the bottom. Okay, so my moles of calcium bromide will go away, and this is stoichiometry like we've been doing for a good while now. Okay, so if I stopped here, I would have moles of calcium phosphate. Right? So the last bit is to convert calcium phosphate to grams. And it is 310 grams, 0.18 grams of C3, running out of room, per mole, right? So my moles of calcium phosphate will go away, leaving me with grams of calcium phosphate, okay? So 2.58 grams of calcium phosphate. Okay, so the part that has not changed at all is the mole ratio in the middle. That's where your stoichiometry happens. But we have multiple ways to get into and out of moles. So different paths to the mole bridge and different paths away from the mole bridge. Okay, and I'm sorry, but you got to start using them all. All right. So this next thing is called gravimetric analysis. And basically what it does is we start with two liquids, two solutions, and when we put them together, we get a solid. Okay, this is a precipitation reaction. Okay, and what we can do is then we can collect that solid and we can dry it, and then we can measure how much measure its mass on the balance. And that will tell us some information about how much of each component there was to start with. Okay, so I don't want you to focus too much on this idea of gravimetric analysis because it sounds like a big scary thing. But really it's just a precipitation reaction, which we've been doing for a while. Okay, so let's take a look at how we can put it into use though. Okay, so we have our equation for the precipitation reaction, right? We have a couple of aqueous things coming together to have a solid precipitate. Okay, so it's a precipitation reaction just like any we've been dealing with. So let's take a look at the information in the question. So we are given a molarity. So that tells us that's going to be a conversion factor. And that's the molarity of the Na2CO3, right? And then we're given a mass for the magnesium carbonate, right? 0.5 grams of the magnesium carbonate, right? So I'm going to go from magnesium carbonate and I'm going to use that to find the sodium carbonate. Okay. And then I'm going to use the molarity as a conversion factor to find volume. Okay. So let's go through that process. Right. So first I have my given information. So I want to impress upon you this molarity. That's a conversion factor, not given information. Okay. Our given information is the 0.5 grams of magnesium carbonate. Okay. So we're going to start there. Mg CO3. Okay. And we're going to convert that to moles because I want to go from magnesium carbonate to sodium carbonate. I have to do that through moles. Okay. So first step is to use molar mass to get there. And it happens to be 84.32 grams of magnesium carbonate. Okay. So if I stopped here, my grams will cancel, and I would have an answer that is moles of magnesium carbonate. Now that I know moles of magnesium carbonate, I can do a mole ratio. So there's 1 mole of sodium carbonate for every 1 mole of magnesium carbonate. Right? So moles of magnesium carbonate will cancel, and if I stopped here, I would have moles of sodium carbonate. Okay? Now, remember our molarity of sodium carbonate, that's a 2CO3. That's the same thing as saying 0.1 moles of sodium carbonate per liter, right? So right now I have moles of sodium carbonate on top, and if this is a conversion factor, that means that I can flip it however I need. So I'm going to write a conversion factor that gets rid of the moles of sodium carbonate. So I'll put the moles on the bottom. My technology will stop arguing with me. And put the liters on the top. Okay, so I'm going to erase this bottom bit so that I can write the answer. All right, so my moles of sodium carbonate will go away, leaving me with an answer in liters. And we do that math, and we should end up with 3 sig figs, 0.0593 liters. Okay, but here's your stoichiometry. And then over here we use molar mass to get to moles, and over here on the right we use the molarity as a conversion factor to get out of moles. Okay. All right, last one. Okay. So when zinc metal reacts with hydrochloric acid, it produces zinc chloride and hydrogen gas, as shown in the equation below. What volume of 6 molar hydrochloric acid is necessary to produce 420.3 milliliters of gas at STP? Okay, let's take a look at the information in this problem. Okay, so remember, anytime you see that capital M, that's going to be a conversion factor. We're not going to start with that. Okay, that's going to be used somewhere in our problem, but not to start with. Okay, what we do have is we have a volume and we have a temperature and a pressure. Right? And it's a gas. Right? So PV equals nRT. And we've got the pressure, the volume, the temperature, and R is a constant. So that's going to get us to moles. Okay, so that's where we're going to start with this problem. So we need our milliliters in liters for our gas problem. Because the units of R are in liters. Right? And then the rest we have 1 atmosphere and 273 Kelvin. That's STP. Okay, so let's go ahead and rearrange PV equals nRT and solve for N. So the number of moles equals PV over RT. So the number of moles is equal to 1 atmosphere times our volume, 0.4203 liters, divided by the gas constant, liters, atmospheres over moles, Kelvin, times 273K. Okay, and we're going to calculate that super fast. 206 times 273, and we have 0.24203 divided by the answer. So we should get 0.01863 moles of H2 gas. Okay. So that's a bit of a trek, but this is one of our paths to the mole bridge. Okay. So I'm going to bring that number down to the following slide because I've got more blank space down there, and then we can do the stoichiometry, okay? So we start 0.1863, and that should be, looks like 3 sig figs. So let's keep track right there. Moles of H2. Right, now I'm in moles, so I can go straight to moles of the other things. So I'm going from moles of H2 to moles of HCl. Right, so there's 1 mole of H2 gas for every 2 moles of HCl. Right? So times 2. Right? So if I stopped here, I would have moles of HCl. But now we're going to use this conversion factor to get to a volume. Okay? So I've got 6 moles of HCl per liter. Okay? That's my 6 molar part, conversion factor part. Okay? So moles of HCl will cancel. Okay? So let me double check our answer, divided by 6. Right. So we should end up with, take this out of the way. So we should end up with 0.00621, which is slightly different than what the slides say, but pretty darn close. I'm close enough. Close enough for comfort. Okay. All right. So this, I believe this does it for us. It sure does. Okay, that's our last slide for this chapter, right? Please make sure to ask me questions, shoot me emails, join the office hours. I want to help, and this stuff gets a little complicated. So, but the biggest challenge, as usual, is interpreting these word problems, all right? So